Quiz to match with your perfect.
We're going to be getting started shortly. I know people are still streaming in, but I'd ask if you could please find a seat. And we're going to start the program for the von Kármán lecture shortly. Apparently some of the other sessions are running a little late, and so people are still streaming in, but we are going to get started on time. So we're going to give it about another minute or so. Well, good evening. My name is Chris Pestak. I'm with the University Space Research Association, longtime member of AIAA, and I'm pleased to present our featured speaker tonight. Before we do, I'm going to go over a few housekeeping items. First of all, thank you for being here for the von Kármán lecture in Astronautics. As you have seen on the slide over here, this presentation, in addition to you folks being here, is also being streamed live over the AIAA network, if you will. It's able to be seen in other locations here, and it's going across the web. And we will be accepting questions not just from people in the room, but also anyone who's online watching. And in the slide over there, you see the link to go to that, where there are a series of questions. As people ask questions, you can add on to that question and decide that's one you want asked. And what I'll do is, when we get the questions, we're going to have about 10 to 15 minutes for Q&A afterwards, where we will take the top-rated questions in terms of the ones that people want answered most, and we'll address those to the speaker. Second, all of our speakers' bios, including Dr. Bob Fugate, are available on the AIAA Space Forum website, the link. And finally, following tonight's session, we have, there's going to be the reception over in the exhibit hall. And so there will be some announcements after the lecture. Dr. Fugate's going to give his presentation, and then there will be a presentation of an award to Dr. Fugate. And then we'll head over to the reception after the Q&A. So good evening, and welcome to the von Kármán Lectureship in Astronautics. The von Kármán Lectureship is a unique forum to celebrate discovery and accomplishment, and was named in honor of Theodore von Kármán, the world-famous authority on aerospace sciences. It showcases a person who has performed notably and distinguished himself technically in the field of aerospace sciences, and our lecture has done that. I am very honored to introduce Dr. Robert Q. Fugate, the presenter of tonight's lecture. During his distinguished 36-year career with the United States Air Force from 1970 to 2006, Dr. Fugate pioneered the research, development, and application of advanced technologies in the areas of atmospheric propagation physics, atmospheric compensation using laser guide star adaptive optics, and the acquisition, tracking, and identification of objects in space using large aperture ground-based telescopes. Originally from Dayton, Ohio, Bob earned his BS in physics in 1965 from Case Western Reserve University in Cleveland, Ohio, and in 1970, he earned his PhD in experimental physics from Iowa State University. I could read you his list of awards and recognitions, but I would be up here for the entire time. That would take too long. So I'll just mention to you the one that I found the most interesting, and it's the most telling about Bob's contributions to the astronomy community. In 1997, asteroid 6770, which is out there in the asteroid belt, was renamed 6770 Fugate in his honor. I believe you're going to find his lecture interesting, enlightening, and compelling. So without further ado, please welcome Dr. Bob Fugate.
Thank you, Chris, for that great introduction, and thanks to AIAA for this opportunity to tell you about laser guide star adaptive optics. You know, I have to tell you, as a ground-based guy, I'm feeling just a bit nervous talking to a room of space experts, but I hope to explain why astronomers today are very excited about ground-based telescopes and how those telescopes can complement space telescopes. What we see in the picture here is the first laser guide star AO system on a 1.5 meter telescope at the Starfire optical range at Kirtland Air Force Base in New Mexico. This facility was very instrumental in advancing the technology, and perhaps most importantly, in transitioning it to the astronomy community. And I hope to give you a flavor of that history. Okay. Before I get started, I want to tell you a quick story. In 2006, at the SPIE Telescopes and Instrumentation Conference in Orlando, Florida, the full-scale model of the James Webb Space Telescope was on display in the parking lot of the hotel. I ran out to get a picture of it, but there were two fellows from the European Extremely Large Telescope Project out there looking at it. They were walking around, reading the placards, looking it over, and finally one said to the other one, "But it's so small," which is not an unreasonable comment coming from someone working to build a 50-meter telescope. So, why do astronomers want these big telescopes? Primarily for two reasons. One is resolution, and the other is sensitivity. Sensitivity being the inverse of the time it takes to reach a specified signal to noise in an observation. And what's, you know, all the way from the Big Bang to the present, there are a lot of unknowns and very interesting puzzles in the universe. So what's interesting is the sensitivity in particular. Here are some numbers with respect to an 8-meter telescope, which are quite a few of today, for a 30, 39, and 50-meter telescope, and for two conditions. One, seeing limited, that is limited by the atmosphere, and the other one, diffraction limited. And what you'll notice is in the diffraction limited case, which is one of the reasons we go to space, is that sensitivity goes as d to the 4th. And so that's a huge increase in sensitivity. So I think we're all familiar with the difference between something in space and something on the ground. Here's a picture of the trapezium, and I'll feature it in several examples during this talk. One made by the Hubble Space Telescope and one made with an 8-meter telescope on the ground. So the 8-meter telescope may have more sensitivity, although I kind of doubt it. But it clearly has much less detail and information in it than the space-based image. So what's going on? If you have a diffraction-limited telescope, the resolution is basically lambda over d. So if you want more resolution, you just make the diameter bigger, or if it's convenient and worthwhile, you can make the wavelength shorter. If you're on the ground, however, you have this situation. Here comes our perfect plane wave that's been traveling through the vacuum of space for 12 or 13 billion years, and the last millisecond of its journey, it goes through the atmosphere and gets totally screwed up. And that atmospheric medium is regions of different temperature and thus different refractive index. And so part of the wave gets behind. There's a phase delay, and the wave front becomes aberrated in a very complex way. And so when the telescope tries to focus it, it gets all messed up. You get a big blob, and now the resolution is no longer limited by the diameter of the telescope, but it's limited by this parameter R0, which is a characteristic of the atmosphere. And it's typically a diameter that represents how big the telescope can be to make a diffraction-limited image, and that's like 15 to 30 centimeters. So we see that we get the same blurry image that with an 8-meter telescope that we can get with a 14-inch telescope. We just get this image a lot faster, as the sensitivity is a lot greater. And it's interesting that Isaac Newton recognized this in 1700, and I love the way he described it. Long telescopes may cause objects to appear brighter and larger than short ones can do, but they cannot be so formed as to take away the confusion of the rays which arise from the tremors of the atmosphere. So, you've heard that Isaac Newton was a brilliant guy. He really was. Well, 250 years later, an astronomer at Palomar Observatory proposed a way to fix this problem, and this is really the foundation of modern adaptive optics. If you read this paper, which is published in 1953, it has all the elements of a modern AO system. It has a wavefront sensor, and it has a wavefront corrector, and it has some sort of feedback that changes the wavefront corrector based on the sensor. Now, the technology that he was proposing, which was writing electron beams on a thin film of oil, which was, by the way, trying to be used to build an outdoor television system, just wasn't up to the task. But the way this would be implemented is you would put these components in the reduced space of a telescope so that light from the object would be sampled by the wavefront sensor, and then with the proper processing could be in real time fed back to a wavefront corrector that we call a deformable mirror. And if you can instantaneously almost put that figure that you've measured on the mirror, actually the conjugate of that distortion, when the distorted wavefront reflects off the mirror, all the distortions being registered properly, of course, you get back to the plane wave you had when you entered the atmosphere. And the rub here is this has to be done hundreds or even thousands of times per second. And so you have to have the technology that supports those kind of speeds. So the first real on-the-sky kind of system was all passive, and it was built by the company ITEC under DARPA sponsorship, or ARPA at the time, and put on the ARPA Maui Optical Station 1.6 meter telescope, a special telescope with 3 axes that was designed to track low Earth orbit satellites. This was truly a heroic effort. The equipment weighed more than a ton. It used photomultipliers for the wavefront sensor. It had a 168 actuator high voltage deformable mirror, which is basically a solid block of piezoelectric material operated at about 1,000 volts with interspersed electrodes. But it only worked with bright targets. And because most of that light from the target was being used to run the wavefront sensor. So what was really needed was some kind of an artificial guide star that was always bright anywhere in the sky. Well, Julius Feinlieb, who was a fellow working on the project at the time with ITEC, was standing out on the ground there at Maui one night, and they had a LiDAR that pulsed at like 1 hertz that sampled the atmosphere for transmittance. And when he saw that, he said, maybe we could use the Rayleigh backscatter from that laser in order to make a wavefront measurement for the adaptive optics system. So that was the basis of his idea. And in the fall of that year, he called a meeting together of government people. I was fortunate to be at that meeting, along with David Fried, who, the guy that invented R0, as well as, by most arguments, is the world's expert on atmospheric turbulence, and some Rhett Benedict from DARPA, and some other AFRL folks. David Fried immediately, when he heard the idea, said it wouldn't work because it was only sampling part of the atmosphere. He went off that very night and stayed up all night trying to do the analysis, couldn't solve the equations, but he came back after he did numerical analysis and said, this may not be so bad after all, especially for small apertures because of an effect that he called focus anisoplanetism. And I'll show you a diagram in a minute. Well, the Jasons heard about this, and in the spring and early summer of 1982, we were summoned to La Jolla, California, to explain to them this concept. And as most of you know, this is a very high-powered academic group. The chairman of the panel was Will Happer from Princeton. And when Fried explained focus anisoplanetism and that it had its limitations in terms of correcting large apertures, Will said, well, why don't you build a laser to resonantly excite sodium atoms in the mesosphere? So I looked over at David, and David looked over at me, and we didn't know what the heck he was talking about. So it turns out, there's this layer, and this is not a very good rendition of it from the space station. If you look around, you'll find some. This has got a lot of air glow in it. But so there's this 10-kilometer thick layer of sodium atoms, a few thousand per cubic centimeter, not very many, that hang out at 90 kilometers and is replenished by meteors. So if we could shine a laser up there and excite those atoms and look at the return light, we could use that as a beacon or as a guide star. And so this is kind of the diagram. Here's your aperture. A Rayleigh beacon has a large divergence, basically, because it's at low altitude, whereas a higher altitude beacon more closely matches parallel rays coming from infinity. And that's the idea. So the error that you make here is partially corrected by making the beacon higher. So Rhett Benedict from DARPA immediately said he was going to sponsor 2 experiments, a sodium experiment and a Rayleigh experiment. I immediately raised my hand and volunteered for the Rayleigh experiment because I had a laser that I thought would work. And unfortunately, MIT Lincoln Laboratory got stuck with a much harder experiment because they spent over a year with a contractor, Avco Everett at the time, to try and build a laser that would excite sodium. You can't make sodium laze because its half-life or its lifetime is too short, and it's impossible to get a population inversion going in sodium vapor. So it turns out the program became classified. It became so classified that there were probably less than 100 people in the country that knew about these experiments and this concept. And the other thing we learned was pretty soon from analysis that you couldn't get any tilt information about atmospheric turbulence from the laser guide star because you didn't know where it was in an absolute sense, in an inertial reference sense. So we would still have to measure tilt using a star or a satellite or some other inertial object because the laser goes up and you don't know where it ends up. And in fact, if you look through the same aperture you propagate it from, it never moves. It comes right back down the same path. But that's not a problem because you can use the full aperture to measure tilt. Whereas in order to measure wavefront aberrations, you need to break the wavefront up into sub-apertures and measure the tilt or the direction each one is traveling. So here's a couple of pictures. By the way, the only picture made of that first experiment at the Starfire optical range in which we tried to determine could you use Rayleigh backscatter to measure atmospheric distortion. And sort of a very crude setup. We ran stuff with the covers off all the time because we had to keep it running. It was done on a shoestring, basically. And this is an example of the measurement. So we had 18 subapertures that were used to separate spots from both the basic idea in the experiment was shine a laser at a star, look at the backscattered laser light with a range-gated sensor. The laser was pulsed, so you only looked at the light coming from some high altitude. And then measure the light coming down from the star. And look at the wavefront from each one of those sources and compute the difference. And does it follow the Fried theory that said the error in using the laser increased as the 5/3 power of the aperture diameter? So here's an example of the spots from the star and from the laser. And when we reconstruct the wavefront and look at the difference, the dashed line is the theory, and shown in the other lines are 2 sets of measurements. And so we were kind of overjoyed. This was a very important chart because it said we kind of thought we knew what we were doing. About this time, Charlie Towns, Professor Towns from Berkeley, was briefed into the program, and he actually made several visits to the SOR. He was very interested in atmospheric fluctuations because some of you know he was building interferometers. And he also became very instrumental in helping the Air Force to get this declassified when it became clear that that was going to be the right thing to do, to share this technology with astronomy. It was about a decade after we did these first experiments. And so he also chaired the first session where this was publicly released at the American Astronomical Society meeting in Seattle, Washington in May of 1991. And this is a picture that someone made of me, Bruce Goldberg, giving a talk at the press conference which followed the briefing. And you can see Professor Towns and Charles Premmerman from MIT Lincoln Lab, who reported the work on their sodium experiment, which was done at White Sands Missile Range in southern New Mexico. So it's kind of cool that both of these experiments were done in New Mexico. At least it's kind of cool for me because that's where I live. And then in September of that year, we published these results in Nature. And volume 353, I think. It always amazed me that I was publishing in a journal that Isaac Newton published in. Not that, you know, but it was just kind of cool. But the editors, who were really in general pretty stuffy, they kind of lightened up and used this picture in their editorial again, this laser guide star system picture, and titled the article, "Beam Me Up, Scotty." And then in March of 1992, we had a workshop in Albuquerque at Kirtland Air Force Base in which we invited astronomers because we wanted to offer this technology to them because we knew it was going to be a boon for astronomy. And 250 showed up. And they had already started thinking about this, and we had quite a few talks, and I was able to get Horace Babcock to come to the meeting and give the keynote. And when he got up, the first thing he said was to this crowd of 250 astronomers, "What took you so long?" Because, you know, he proposed the idea in 1953, and now it's 1992, almost 40 years later. But we had 3 nights of demonstrations on the 1.5 meter telescope with the copper vapor laser out at SOR, and I think it kind of endeared us to the astronomy community, and we've had a great relationship with information flowing back and forth ever since. If you want to read more about this, there's a book about the history of the military contribution to adaptive optics written by Bob Duffner, who is the historian at AFRL. And he said he wanted to grab people when they walked by the bookshelf in the bookstores, and so he put a picture of me on the front cover when I was 12 years old with my cardboard telescope in Dayton, Ohio. What I like is the cuffs on my pants here. Must have been a really styling deal then. So for about a decade, we continued operating the 1.5 meter telescope with this copper vapor laser. Ran at 5,000 pulses per second, and we learned a lot of stuff. We also shared this with the astronomy community. We had a program at the National Science Foundation in which they funded astronomers to come out and use the telescope and the equipment that we had in order to make scientific observations. We published quite a few papers, refereed papers in astronomy, and so it was quite successful. And so here's an example of some of the early sciences. This is an observation suggested by Peter McCullough. This is again the trapezium. And this is with a hydrogen alpha filter, and this is with a continuum filter. And so everything you see here that you don't see here is ionized hydrogen. And look at all these little guys that aren't quite stars yet. Pretty cool. Now, when you compare that to the Hubble image, sorry these aren't bigger, you know, there's still a lot more detail in this than there is in this. But you know, this is a 1.5 meter telescope in the desert. This is a 2.4 meter diffraction limited telescope in space. This is a few $100,000, and this is more than that. And here's our picture of Saturn. We actually used the laser guide star for this because Saturn is so huge that it overfilled all the subapertures in our wavefront sensor. And so we just decided to try, we were actually looking for Comet Levy, I think, at the time. And it kind of fizzled for us, but in the morning we had a bonus, and that was being able to image Saturn. And some of the planetary astronomers said at the time in 1994 this was one of the finest ground-based images of Saturn they'd ever seen. And then we started cutting our teeth on imaging satellites, which was really what the Air Force mission was, space situational awareness. And here you see from open loop, correcting the tilt only, to low bandwidth and high bandwidth AO, and then down here you see some deconvolved images where we try to improve the higher spatial frequencies. And this is the satellite CSAT. I'll show you another image of 3.5 in a minute. And then this, you know, what's important, especially for astronomy, is can you maintain the operation of this adaptive optics for long times, especially correcting the tilt. And this shows long exposure images, long exposures being 10 and 20 seconds of a star. And if you're in the front row and the projector's good, you might be able to see the airy rings around these. And then I got a call in July of 1997 from Jim Breckenridge at JPL in a real panic one afternoon. And they had been instrumental in building the payload for the Japanese audio satellite, which had gone silent. And there were reports of some disaster in space. And so could we look at it? And so that very evening, when the satellite went over, we ran this adaptive optics on the 1.5 meters, and we got these images in our acquisition camera. I suggested we use the science camera, but Jim said no, he wanted a video. And I called him up right after the pass and was describing what I was seeing, and he kept saying, "Oh my God, don't you see the solar panel deployed along the boom?" I said, "No, I see two things that look like a cylinder at one end of the boom." And so it turns out that apparently the solar panel latches had failed and it had rolled up like a party favor and become $2 billion worth of space junk. So I think one lesson learned here was in redesigning the latches on the solar panel. So while we were learning how to use laser guide star adaptive optics on the 1.5 meters, I was over in the director's office campaigning for a bigger telescope because my long-range vision was a sodium guide star on a 3.5 meter, well, a 4 meter class telescope. You know, it was an interesting story. The day we got the 1.5 meter telescope, the day after actually, I went into the director and he said, "Well, I see you got your telescope." And I said, he says, "What's up?" And I said, "Sir, we're going to need a bigger telescope." And he threw me right out on my ear. But I kept going back, and I wanted to take advantage of the spun cast mirror technology, which was the only way to make a big mirror at the time, that had been invented by Roger Angel at the Stewart Observatory at the University of Arizona. And so we helped them fund stress lap polishing, and it was a very collaborative effort. And at the time they made this mirror, all of the guide star stuff was still classified. So it was a very fruitful collaboration. I also worked on getting the key components together to run the adaptive optics for the 3.5 meter. Some of those key components are, probably the most key is the CCD-based wavefront sensor chip that was built by Lincoln Laboratory. It has multiple readouts, no waiting, and this thing would run at several thousand frames per second at a few electrons of read noise at 80 or 90% quantum efficiency. And here's the deformable mirror, which is another key component, of course. This is a 941 actuator mirror, a 1 millimeter phase sheet. And this was a different technology, lead magnesium niobate, electrorestrictive actuators instead of piezoelectric. And so it ran at 70 volts. We had to build all of our own electronics in-house, mostly based on field programmable gate arrays because it was all specialized processing. And you know, it fit nicely into a garage full of racks, which we got a little grief about, but it's what we could do at the time. So in the fall of 1997, we got that system running. It had been quite a few years since we got the telescope because budgets were much leaner and it was more piecemeal. And then in the early 1998, we really got the system tuned up, and it could do a Strel of a half at 0.8 microns. And here's an example image. So here's what it looks like in real time, or what it looked like in real time. There's the higher order loop closed. There's it says a binary star, a 0.2 arc second binary. We open the track loop here, and you can see how much tilt there is on the system, and how important it is to get. Then we close. Now we've got the higher order loop open, and then we open both loops, and now we see the wandering around. Maybe we'll go through that again. So first you'll see the track loop close there, and then the higher order loop close there, and then the track loop open. So it's very important to control tilt in these AO systems because that's where most of the power is in the spectrum and so forth. And then here's images of CSAT with the 3.5 meter telescope. These are a sequence of still images from a science camera, unprocessed, post-processed, I should say. And remember, this is 1998. It would be really great if I could show you what we're doing now. And here's a couple of closer looks at those images. This one is now deconvolved. And what we noticed was, based on the drawing that we got from JPL, although we couldn't find anybody to talk to about it, was that one of these scatterometer antennas was missing, and this little telemetry dish was missing. If you're able to look at the original images on a computer screen, it's very obvious. So we called up Space Command and said, what's up? And they said, well, we don't know, but we have seen a couple of objects drifting away from this satellite over the years on radar. So this satellite, as some of you know, failed early on in its life, so maybe it was cursed at birth, I don't know. And here's an example of some more post-processing with two different methods for deconvolution. This is Ganymede, and here's our in-house astronomer at the SOR, Jack Drummond's result, and here's one in a sponsored program from the Air Force Office of Scientific Research. What's important here is that these two look very similar. So, you know, I often, being an experimentalist, look at what they do in theory with deconvolution and think it's a black box. But in this case, they're turning out very, very similar. So by 2004, we had solved the how do you build a laser to excite sodium problem, since you can't make sodium lasers. I'll tell you about that in just a second. And here it is installed on the 3.5 meter telescope. This is the laser optics here, and the control electronics over here, and the launch telescope along the side of the telescope. Here's what it looks like in the sky. So this is the vision I had in 1982, was a sodium guide star coming out of a 3.5 meter or 4 meter telescope. Took a long time to get there, nearly 20 years. So you got to take risks and be persistent in this business. One of the things I learned. And so here's the configuration. Here's the fast steering mirror, which I failed to mention earlier, that corrects the tilt. And here's the deformable mirror, and then we pick light off for the tracker, which has to, again, use a natural object like a star or a satellite. And the wavefront sensor for the sodium light goes in here, and then the science cameras after the compensation. And for the 3.5, we propagate the beam off the side of the telescope, but for a large aperture telescope, like an 8 or 10 or 30 or 40 meter telescope, you need to come out from behind the secondary, or you need to make an asterism of guide stars, as I'll tell you in a minute. That prevents what we call perspective elongation of the laser guide star in the wavefront sensor camera that's looking at the edges of the aperture, because the sodium layer is 10 to 15 kilometers thick, and if you're actually looking at that sort of from the side when you're out here 15 meters away, and it matters. So here's what it looks like to the telescope. We're not interested in all this Rayleigh scatter, of course. We're only interested in that round dot at the end, which represents the guide star. And so we put a field aperture in the wavefront sensor in order to eliminate the Rayleigh backscatter. So this laser is a really interesting story in nature, in that the two strongest lines of neodymium YAG, when mixed in a nonlinear crystal as a sum frequency system, generate a line that's exactly to about 5 digits what you need to excite mesospheric sodium. So I always thought somebody is saying, use sodium. I mean, this is an incredible coincidence. And but this is not a simple laser, because you want to have this cavity, this some frequency cavity, doubly resonant. It has to be resonant at 1064 and it has to be resonant at 1319. So you need feedback to control the frequency of one of the two lasers to lock it to the other one. And so it gets to be complicated. This is the 1319 leg of the laser. It has 6 laser diode pumped cavities that generate the 1319. And there's a similar one for the 1064, but it only has 4 laser pumps. And today, however, we have some new technology that's very efficient and very reliable. And there's a company in Germany, TOPTICA, that is generating this as a commercial product for use by astronomers. And it's based on a Raman fiber amplifier and second harmonic generation outside the laser cavity or outside the fiber amplifier. And here's a picture of some of their equipment, and the astronomy community has become very interested in this. And they have recently deployed the first one of these at the 8-meter telescope at the VLT at Paranal in Chile. So let me review really fast the improvements in deformable mirror technology. This is a picture of one of those monolithic piezoelectric mirrors used in the compensated imaging system back on Maui. You know, hundreds or a few thousand even volts. And this is that 941 actuator mirror that we first used on the 3.5 meter. Since this mirror, Zynetics has built a much more robust version that has more stroke and that you can update at 10 kilohertz. And then they've modularized this approach and made smaller actuator spacing with some loss in stroke. But there is, this one is 1,396 actuators. There's a 3,000 actuator version of this on the Palomar telescope. And now we have MEMS devices. These are very small, but they need to be used in conjunction with another higher, I should say lower spatial frequency deformable mirror. So it's kind of like a woofer and a tweeter. You need some basic cleanup with a conventional deformable mirror before you go to this system. And so this does really fine, delicate cleanup, and it's used here very effectively in the Gemini planet imager, which we'll talk about it more in just a minute. So this is a system that's designed to look for exoplanets, and it's installed with a coronagraph on the 8-meter telescope in Chile. And these are some of the first light images. And then another really incredible innovation from the astronomy community, it really started at Stewart Observatory at the University of Arizona, is an adaptive secondary mirror. And so here you see a 1.2 meter mirror that has 672 actuators. This is one of the 2 mirrors on the large binocular telescope. These are permanent magnets glued on the back. This is a 2 millimeter thick shell of glass, and they're making them 1 to 2 meters in diameter. And let me tell you, they've broken more than one. And it is suspended only by this center hole and hangs under a base structure full of electromagnets. And by changing the strength of the electromagnets, they deform this mirror. The great advantage of this is, so it sits right here at the secondary of the 2 mirrors in the 2 8-meter telescopes. And the really great advantage of this is you can literally have 3 surfaces between the sky and your detector. And so, again, the astronomers are very, very interested in sensitivity. Here's a picture of Theta 1b in the Trapezium again. I tried to stay on that topic. So this is one of the stars in the Trapezium, and you can see 2 stars here, 1 here and 1 there, and quite a few airy rings. And so I remember a comment by one of the astronomers, what are we going to do about these damned airy rings? That's supposed to be a joke, folks. So originally I said size doesn't matter on the ground, but if you have adaptive optics, it really does. Here's that 14-inch telescope. Here's the 1.5 meters with the laser guide star AO. Here's the 3.5, and here's an 8-meter telescope, albeit at 2 microns. These others are hydrogen alpha wavelengths. But we're getting increased resolution and we're getting increased sensitivity as advertised. So this image, which was exposed less than a minute, gets to 19th magnitude, for instance. So today we have everybody on the bandwagon, so to speak, and people are installing laser guide stars on all their big telescopes. And coming in the future, we'll have a next generation of AO at Keck, the LBT, which we've talked about, 2 8-meter telescopes, the giant Magellan telescope, which is 7 8-meter telescopes on a single mount, 30-meter telescope, which is 30 meters, and the European extremely large telescope, 39 meters. So here's some pictures I've gotten in my collection of what people are doing. The most recent is this one from the VLT in Chile, and shows that Raman fiber frequency doubled laser. So I just wanted to show you a little bit about what they're doing with this stuff. This is a picture I took over at Keck. This is the secondary cage, and this area here is the launch telescope for the laser guide star. It's a 50-centimeter telescope. This item up here is a passive transponder antenna that's used to find aircraft based on their transponder signals and avoid, illuminating an aircraft with the laser. They have lasers on both of the 10-meter telescopes at Keck, and as I'll show you in a minute, one of their primary research objectives is the center of our galaxy, where there's a supermassive black hole. And this shows the performance of the natural guide star using stars alone, and how that's extended by using the laser, which increases the sky coverage, especially off the galactic plane, where there are much fewer stars. So here's some images at 2.2 and 1.6 microns. Uranus, these are kind of old images, but it shows you open loop and closed loop. And here's Neptune. And so the question early on was, are we really getting what we deserve in terms of resolution? And so they did a lot of comparisons initially with Hubble, especially at the same wavelength. And here is Uranus again, an IR image compared with a visible image. So here's a laser guide star compensated image of the center of the galaxy, and that little arrow shows you where the black hole is. Of course, you can't see it, but look at these nice, and the area rings here are hexagonal because the shape of the mirror is a hexagon. And Andrea Getz at UCLA and her galactic group has made just incredible scientific advancements by plotting the orbits of stars around the black hole, and from that she's been able to determine the mass being equal to 4 million suns. I mean, she has more than one significant digit. But she's a great proponent of laser guide star adaptive optics because none of that could have been done without it. Here's a couple of more examples, again, where they're comparing Hubble and the Keck, again at the same wavelength, and where you can, where you are getting the resolution you think you deserve. And then, of course, one of the holy grails of astronomy is exoplanets, and can we detect life somewhere else in the universe? In 2008, in HR 8799, 3 planets were discovered at Keck. Say a little bit more about that later. So one of the problems with all of this is, you've heard me talk about focus anisoplanetism. There's another kind of anisoplanetism, there are lots, but the other one we call ordinary anisoplanetism, if you can imagine such a thing. So here's an image from the 3.5-meter telescope at the SOR of a binary star. These stars are 7 arcseconds apart. They're about the same brightness. These numbers represent counts in the camera. And so we close the loop on this star, but you'll notice even in this picture, this one is weaker. It's not as well corrected. And so I took 100 pictures like that. These are magnified now, so we can see them in more detail. And these are now the counts. You can compare 26,000 to 376. This is where your sensitivity comes up, right? Up here we have the worst, the average, and the best image 7 arcseconds away. And so that's not very good. That's not very much distance, angular distance either. So here's the ordinary anisoplanetism, and it arises from the fact that when you look in two different directions, like at the binary star, you're looking through two different parts of the atmosphere, and over a fairly small angle, a few arc seconds, the atmospheric distortion becomes decorrelated. And so you have a very narrow field of view system that has limited use, perhaps. Well, today the astronomers are tackling this problem, and they've done so very effectively. What we've been talking about they call single conjugate AO, but at most of the sites where there's good seeing, the atmosphere is in layers. And so what if I had like 3 layers above my site where the strength of the turbulence is concentrated, if I could re-image 3 deformable mirrors at those layers, and I could control the mirrors to correct the turbulence in those layers, then I could increase the field of view. And this has been done both passively and with laser guide stars now, and the system is complicated, but it works. Another problem is this focus anisoplanetism, and it turns out that if you put up an array of guide stars and you look off axis, you can fill in this cylinder of air above your telescope and calculate, just like in tomography, instant to instant, hundreds of times per second, you can determine what the turbulence is in any given direction. And then, as you'll see in a minute, you can correct in that direction. The other approach is extreme AO, and as I mentioned earlier, if you have something like a MEMS device behind a conventional DM that does coarse and fine, and then you have a coronagraph that blocks out the light from the star that you're looking at and correcting on, you can get very high contrast images of faint objects very close to bright ones. And then finally there's not finally, but another one is multi-conjugate, multi-object adaptive optics. And here again, using tomography, if you know the turbulence in any direction in the field of regard of the telescope, you can put a MEMS DM at that location by picking light out of a field and correct in that direction. What you do is you command the mirror open loop, and the MEMS devices have little to no hysteresis, and so that's very effective. And so I can look now at a cluster of galaxies and do compensated imaging on each one of them. Here's an example of multi-conjugate AO. This is a system on the Gemini South telescope in Chile, and it has 5 laser guide stars, 3 deformable mirrors, and a partridge in a pear tree. And here's a corrected field that's nearly 1 arc minute square. And when you look at the details of this image, the performance out here is 95% of what it is in the middle. And here's the the extreme AO system on the Gemini planet imager using the MEMS device. They're now surveying 600 stars for exoplanets. And just this month, they've actually discovered one that hadn't been discovered either by some other means before. And they have spectra on this planet in 2 bands and confirmed by Keck. This is a Keck image here at 3.8 microns. You'll notice this is not nearly as nice an image as these because this is a very specialized instrument designed to do this. And these spectra are showing strong methane and water vapor absorption. So, what we'd like to see, of course, is carbon-based life somewhere by looking at this sort of science. And so the next generation of adaptive optics at Keck will use multiple guide stars, and here's that field system, and this shows you what they expect in increased performance. And finally, I'd like to tell you about the new extremely large telescopes, 3 of them. This is the giant Magellan telescope to be built in Chile. This is a very hard telescope to make. These off-axis segments that are 8 meters in diameter, if you can imagine, all have to be very precisely made because they're off-axis segments, and so the tolerances are enormous. But they've made 3 of them so far, and it looks very good. These are being built at Stewart Observatory. The 30-meter telescope will be located on Mauna Kea, and this is kind of the artist's rendering of where it is in relation to Keck and Subaru and others, and a picture of the laser guide star constellation going out behind the secondary. This telescope has 492 1.4 meter segments, 30-meter Naismith platforms with 8 instruments. Adaptive optics is built in from the beginning, and this shows the arrangement of that in the building. And some of the simulated results compared to, for instance, in the Hubble Deep Field imaging. Here is Hubble Space Telescope, and here's the 30-meter. And here's a simulation showing the center of the galaxy, this with the current Keck system, this with the next generation of Keck at 8 meters, and then this with the 30-meter telescope. And the bottom line is, how many stellar orbits can you get out of this? So there's lots of science to be done with the 30-meter telescope in that cosmic timeline right from the Big Bang out to the present. The ones I like are nitrogen geysers blowing in the wind on Triton and methane rain on Titan. Pretty cool. And this shows how the 30-meter telescope will be complement the JWST, other space assets, and ALMA, the microwave telescope in northern Chile. I'd like to comment that this was provided by Brent Ellerbrook at 30-meter telescope. Brent used to work with me at the Starfire optical range. And you know, we talked about transitioning technology. The best way to transition technology is through people. And now that Brent was initially in charge of the adaptive optics at 30 meters, he's now in charge of the entire instrument suite. So I'm like a proud dad. You know, this guy is really doing great stuff. And by the way, he's absolutely brilliant. So here's an artist rendering of the extremely large telescope at 39 meters in Chile. And this is how they put out their asterism of laser guide stars. So I started with a picture of the 1.5 meter system at the SOR, and I'll end with it. This one by a professional photographer, Roger Resmeyer, a National Geographic guy. And you know, it's ideas that change the world. And I'm beginning to believe that laser guide stars might be one of those ideas. And until we can put really big telescopes in space, I think telescopes on the ground using this technology are going to be a great complement to those space telescopes. And it's just been great being a part of it. Thank you very much. Okay.
Thank you very much, Bob. Well, on behalf of the AIAA, we have a presentation for Bob, and then we're going to take a few questions. So first, I feel a little bit like the Wizard of Oz here. We have a medal, and not just anybody gets to give the von Kármán lectureship. And so this is the Theodore von Kármán medal. I'm going to present it. We also have a, excuse me. We also have a, I don't know what the word I'm looking for is.
Certificate.
Certificate, yes. Certificate, the von Kármán lectureship in aeronautics to Dr. Robert Q. Fugate.
Great.
Now we're going to, we have time for a few questions, and we've received questions from the audience, and so, Carol, could you get those to me? That have been submitted through the website.
I hope these aren't too hard.
Okay, we have, what are the current planned first flight dates for the Giant Magellan telescope, a listing of the telescopes, GMT, TMT, and their comparison in comparison to James Webb? How do these line up with James Webb?
Well, I think I could be wrong, but I think James Webb is due to be launched in October of 2018. Anybody here that know that that's correct? It's correct, okay. And I think the really first science for 30-meter telescope, well, the GMT I think is like 2021, and the TMT is 2022, and the European ELT is 2024. So, you know, it would be better if they could delay, no. No, I think there'll still be lots of synergy.
And a second question we have here is, what is the laser guide star corrected field of view for the first light instruments at the 30-meter telescope?
Okay, the 30-meter telescope has a 2-mirror multi-conjugate AO system. This is basically a pretty incredible instrument. The whole thing is cooled to minus 30 degrees in order for better background for IR observations. And the corrected field to about 70% Strel and K-band is 2 arc minutes. So it's quite large.
And this is a related question. Since you're so tied into the astronomy community, what is the latest on the 30-meter telescope as it relates to the controversy of whether or not it will be built there on Mauna Kea?
Well, as some of you may have heard, there are protests from some of the native Hawaiians about the construction of another telescope, especially a big one. And I think all the parties involved in the construction of the telescope are respecting that. They have stopped construction at the present time. And I think they're trying to have some civil discussions. The governor of the state of Hawaii is involved. We're hoping things don't become violent, but I think everybody's talking at the present time, and something hopefully will be worked out.
Well, that concludes the presentation and the questions. We have one more final round of applause for Dr. Fugate. And now I would ask all of you to join us in the exhibit hall for a reception in there, and maybe there may be a few drinks and things to eat. Thank you. Thank you for your